So welcome everyone to our webinar series of IAC Webinar Series for Spring 2021. As I recommend is you change your name to your name, company, or university. This isn't required, but it makes the Q&A section a little easier at the end. For you, those of you that don't know, my name is Kelly Baber. I am an energy systems engineer at Rutgers University, and I'm the one who coordinates a lot of these webinars. Just a reminder to keep your mics muted except until the Q&A at the end. So we'll do roughly a 30-minute webinar followed by a 15 minutes Q&A. If you have any questions during the webinar, feel free to put them in the chat and we will address them at the end. Just a little plug for our upcoming webinar. It will be Thursday, February 11th at 3 p.m. and it will be presented by CHB TAP and be a basics intro to CHPs, mainly directed at students, but of course, everyone is welcome. On to today's webinar. We'll be learning about peak electrical demand reduction and fluid distribution systems through load shifting using model predictive control. And our presenter will be Rafael, a master's student and one of the 2020 Student Research Award winners from Texas A&M. Rafael, I'm going to pass it off to you.
Thank you, Kelly. And good afternoon, everyone. Like Kelly said, this is Rafael Dugarte. I'm a master's student at A&M, and if you'll wait all for me for just a moment as I try to share my screen. Like Kelly was saying, this is the IAC Webinar series, and I'll be speaking about peak electrical demand reduction in wastewater treatment plants through load shifting using model predictive control. And even though that's a pretty long title, I hope that by the end of this, we'll all kind of have an idea of what's going on here. I work for the Thermo-Fluids control lab at Texas A&M University. And I've also been working for the Industrial Assessment Center for quite a while. Okay, so here's some personal background information about me. Again, I'm a Master's of Science graduate student here at the university. My background is, again, in mechanical engineering, which I also did here at Texas A&M. I've been a pretty consistent student at the IAC. I've been here since September 2016 when I started, and in total I've been to 18 visits and 6 of them have been as a lead student. Apart from that, about 2 years ago, the IAC, I know nationwide, started pushing for us to go visit wastewater treatment plants. And at A&M, we've done about 5 of them. And of those 5 visits, I've been on 4 of them. So I'm pretty aware of what's kind of going on in wastewater treatment plants. And that kind of makes sense because my whole research background is based around working with wastewater treatment plants. And just another interesting kind of side topic about the IAC and what we do here at Texas A&M, at least, we were able to last year go abroad and take some projects in Panama, which is where I went to high school. So that was interesting, and we had fun with the university students there as well. So the objective of this presentation is to basically tell you guys about what I have been obsessing over wastewater treatment plants for the past 2 years. I'll tell you guys what the idea is behind my research and how we've been drawing inspiration from virtual batteries, how we got to finding out about wastewater treatment plants and why they might be good candidate facilities for this specific area of research, and how we're getting there and trying to achieve this goal, basically. So back in 2017, or yeah, between 2016 and 2017, a paper was published by researchers at MIT that basically explained an idea of using connected smart appliances collectively to offer deferred or variable demand back to the grid. So basically explaining an idea that batteries are everywhere, including things that are already connected to our grid, and some of them might be very useful for us to control, right? I'm sure some of you have heard of pumped hydro storage and maybe other types of energy storage, apart from the most basic ones, which is chemical batteries, right? And why we decided to continue to look at this is because the current state of chemical batteries does not provide cost savings at maybe the scales we're kind of looking at. And because a lot of things currently are, the 4.0 industrial revolution, then it makes sense for us to look at connected things that could also be used as batteries. Again, batteries are everywhere, and some of these might be very useful for us to control. And specifically, we're looking at a smaller scale, looking at plants, or trying to find useful plants that have some type of built-in capacity, system capacity in them, that can also benefit from controllable demand individually, and plants that would have quick ramp rates, right? So as we looked at this idea, we thought about, at least for us here in Texas, we thought about quarry process. So quarries where, rock is ground up, sorted, and distributed. A quarry would have all these characteristics, but they're not as ubiquitous as wastewater treatment plants, at least here in the United States and in Texas. And that's why we basically decided to work around wastewater treatment plants and focus on them. Here in Texas, for example, there's more than 3,000 wastewater treatment plants in the whole state that are large enough for us to kind of treat at this level and find some useful capacity and battery capacity out of them if this works. So arriving at the optimization side of things and the demand management side of things, how could this play a huge role in reducing industrial utility costs? Because I know all of you are IAC students. I'm sure we all kind of understand the difference, or the basic difference, between what energy consumption is and what electrical demand is. One of them is the total amount of energy you're using or consuming, and then the other is the maximum instantaneous energy throughput that's going through your plant at any specific time, right? And as many of you may know as well, at least at the industrial level, facilities get charged for both consumption and demand. And within demand, they get charged for their maximum monthly 15-minute average, right? Why would utilities do this at this level, at least at the industrial scale? Well, because there's infrastructure costs related to varying demand capacities and how the infrastructure is connected to a specific plant, and those costs need to be passed on to the plant as a specific demand charge. Again, I'm sure a lot of you guys know this, but we've seen plants here at the IAC for a really long time where their cost associated with demand accounts from anywhere between 20 to 40 and even 50% of their total utility costs. So this is the side of things that we're trying to minimize. So if a plant is not reducing their throughput in terms of what they're producing or the amount of wastewater they're treating, you could still see a reduced amount of a cost if you're able to lower these peak demands. We've seen this over and over again. Here we have a couple of different examples of kind of the energy or the cost distribution in between consumption, demand, and other independent costs. A past lab mate of ours here at the university figured out that even though industrial facilities are not necessarily the best to seek opportunities for consumer-driven load shifting operations, there is a subset of industrial facilities that would work well for load shifting operations. Very similar, actually, to those found in the best group of facilities where load shifting could be achievable, which are churches, K through 12 education buildings and higher education buildings. Now, as we talk more about the kind of next step of things, well, I'll tell you about wastewater treatment plants, some of their functions, outputs, advantages of using them in our study. Even though I'm sure some of you have already gone to visits and have done assessments regarding wastewater treatment plants. And basically, wastewater treatment plants do a great job at removing contaminants from sewage. And this can be industrial sewage, or most commonly, it'll be residential sewage, right? And they turn this flow of sewage into an effluent water stream that can be reintroduced into the natural water cycle. A normal everyday wastewater treatment plant will have three different types of outputs. These will be a clear effluent stream of water, sewage sludge, which sometimes gets produced into fertilizers and other types of materials. And then some of them are also capturing biogas and even using or selling that. For our study, using wastewater treatment plants made sense for three different reasons. They're geographically ubiquitous, so we'll find them here in Texas, up in Alaska, and all over the country. They are uniform in process. So even though I've been to 4 out of the 5 here at the university, IAC, and they all work differently, but in general, their process is about the same, right? And then finally, they're also well understood as from a process perspective. And boiling down essentially what wastewater treatment plants are, and you can see kind of the process of the water coming in and coming out of a plant here on the right, and there's a picture of a wastewater treatment plant on the left. They're essentially just a series of tanks, pipes, and pumps, right? If we set aside the chemical perspective, we're just storing tanks for some period of time between tanks and moving that water from tank to tank as we treat it and as we push it out of the plant. In terms of the chemical side, for just some background information, this is a very kind of straightforward chemical oxidation and biosynthesis process where organic material from residential sites and industrial sites, plus oxygen and bacteria, which is added in the plant, gets transformed into carbon dioxide, heat, water, and the inorganic residue that kind of makes up the biggest part of that output sludge. However, these plants do work within very kind of narrow constraints. Some of these are in the sanitation and health kind of area where the effluent stream will need to be within a very specific kind of total nitrogen or dissolved oxygen level, as well as total suspended solids, for example. There's about 8 or 9 different constraints on the chemical side. And then you also have constraints on the amount of water that's kind of going through the plant, the amount of water that you're pumping from tank to tank, essentially. And then in terms of basic operation, these plants have to run 24/7. There's kind of no stopping them, and they'll process water anywhere between 2 to 60 million gallons of water per day, depending on their size. We've kind of seen here in Texas how really large plants don't necessarily occur all that often, even though there are some exceptions. But more often than not, these are, you'll get distributed plants that are kind of just a median size. And then finally, the retention time of the water throughout the whole process is on average about 20 hours. So the amount of time between when the water is introduced into the plant and the amount of time it takes for the water to go through the plant, it's just about 20 hours. In our case, or in my case and my research, we're trying to use model predictive control, also called MPC, to control the pumps in these plants to figure out if we can save them some money. And what model predictive control is basically is the most general way of posing a control problem in the time domain. It's very easy to see how an MPC works in the time domain. And what it does essentially is compute at every time instant, so let's say at k, a sequence of future control values that will minimize the difference between the predictive control variable and the reference that you've set over a finite horizon. So it'll do this, for example, for 15 time steps into the future. After that, it's only taking that first element out of that sequence and applying it to the actual plant, and then repeating that process over and over again. You can see how that works here. This is the kind of the quintessential diagram for explaining what MPC actually is. And at the top, you can see the reference trajectory. This is set as an objective. And then you have both a measured output of the plant and a predicted output in brown. And then in blue and green, you have a past control input into the plant and a predicted control input. The prediction horizon is the amount of time the internal model of the plant, which is in the controller, uses to kind of, with the outputs of the plant, kind of figure out what should the controller inputs be. It's also called a receding horizon control, for that reason, because it kind of sees into the future internally. And here you have a kind of a block diagram of how that would work, right? You would have a system or a plant that's outputting some measured values, and these are used as inputs into the MPC controller, where there's two different sides. So an optimization side, where you've developed or designed a cost function to try to reduce some variable, and then an internal model of your plant, which you're using to, with the measurements that you're being fed of the system, basically see into the future, minimize that prediction horizon or over that prediction horizon, and then only taking that one time step action and inputting that back into the system and repeating the steps over and over again. Historically, MPC has been used in the chemical industry, in oil and gas, in the production of polymers, and more recently in power system balancing. Here you can see a picture of it being used in the University of Zurich to control a quadcopter. Recently, there's been a lot of use in some of these conferences. You'll see how a relatively large portion of research has to do with MPC. And again, some of the reasoning behind us looking specifically into this area of research is because the intersection between MPC application and research, it being mainly in chemical plants, oil refineries, and power systems, like I said before, and then the wastewater treatment plant research literature that's out there mainly focuses on optimization, but optimization on the controls for dissolved oxygen levels. So there's a big portion of the energy being used in wastewater treatment plants that goes to aerating in the sewage. That's about between 30 and 40% of the energy in a wastewater treatment plant. And thus, a lot of the research that's out there currently focuses on optimizing for the dissolved oxygen levels. So it's more aeration focused. So there's a clear kind of intersection between these two things that's missing, and that's what we're trying to focus on with my research. So boiling down the idea into basically just a sentence, we're trying to strategically control the pumps in a plant to turn on and off if it's for fixed speed motors, to minimize the utility calculated demand over a 15-minute interval, which is how most of these utilities kind of factor that in demand charge, while taking into account both the plant's physical constraints, so the tank height, the fluid tank height, the fluid levels in the tanks, and then the quality and environmental requirements that you kind of need to pass for you to be able to output the effluent stream. And then of course there's kind of also constraints on what you can do with the actuators, in this case the motors, the actuator range, and then the rate of control. On the right, you can see, again, a very similar kind of block diagram to what you saw a couple of slides ago, where you have the model and the controller with their inputs and outputs. And what we've kind of seen as I've done this research is that a lot of it is a balancing game between you needing to, let's say, pump some water as water is coming in, and you deciding to either turn on and off the pumps at different stages throughout the process to maintain some, maintain some demand that you've already kind of decided. And there's different ways that this can be done. Currently, or not currently. In the past, we used a simplified wastewater treatment plant model as a basic first step into figuring out if the MPC controller would work. You can see another block diagram of that plant model to the right. And it was a very basic model design with just some very few components, right? We had tanks, motors, and then valves. And in this case, this was a 4-tank and 2-motor model that we used to determine how well MPC control would work at this kind of level of complexity. At this level, we also used actual physical dimensions of one of the case plants we looked at during our IAC visits. And then we also used their like predetermined flow rates that they run through. That was at Gatesville in Texas, and you can see a picture of me and some of my IAC mates here in the visit. In this first step, we used a varied number of simulated scenarios to see how the controller would work. And we decided to work with, trying to see the difference between how fixed speed motors or variable speed motors would work in different situations. A lot of the plants, or actually most of the plants we've gone to here in Texas, do not have variable speed motors in wastewater treatment plants. They'll all just have fixed speed, which is where we think most of the savings is going to come from, because they're using fixed speed motors. And then we also, as a benchmark, decided to use a simple on-off control and compare that to the results from the MPC to see the difference in demand, in peak demand. And then again, some of the influent data we decided to use, we had to take into account, for example, daily intake patterns for flow rate into these plants, which will vary throughout the day, but then it'll also vary from weekday to weekends, and then it'll vary depending on the seasons and so on. At this level, we've had some preliminary results that aren't super conclusive, and that's why we're taking it basically to the next level to see how the controller continues to function. And at this secondary level, we will be using a platform which was designed in Sweden by researchers at Lund University, which we're in contact with. They've designed this whole wastewater treatment plant model to simulate these kinds of scenarios and see what kind of control strategies work. They haven't necessarily designed this to figure out control strategies in terms of demand, more so what we've seen in the past, which is optimizing for dissolved oxygen and things like that. But we're using it in this sense because the platform's out there and ready to be used. It has a very generic plant layout, which you can see here on the left. That even though it's generic, it's a lot more complex than what we were using in step 1. And then this will be the secondary step. And then in the future, we're looking to continue this research and continue to make the model more complex, and also introduce more interesting scenarios into the simulation to see what kind of savings we can get. Things like comparing rate structures and seeing how that affects the results, and leveraging conventional demand response programs and see how including in that level of complexity would affect the simulations as well. And then applying a more polished controller to more calibrated models of plants here in Texas. And at the end of everything, not only being able to estimate, potential savings at a plant level, but seeing how that would, or being able to estimate potential savings, let's say at a grid level, how if you could implement these kinds of controllers very widely, what kind of benefits, let's say, utilities would have at that level. Thank you guys for listening. I'm here to answer any and all questions you guys have.
Thanks, Rafael. So now we're opening it up for questions.
Hi, Rafael. This is Ryan Edwards. I'm actually an A&M IAC alum. And
okay.
work with quite a few wastewater treatment plants. What kind of feedback have you gotten from from the plant personnel as far as feedback on these control strategies?
So yeah, go ahead.
Yeah, just wondering. In my experience, they've been hesitant to adopt new operation strategies for energy optimization.
Yes.
So just wondering what your experience with that has been.
I think I would agree in some part with what you're saying. Through the 4 different plants we've gone through, there's a very mixed bag of plant operators and how they kind of see things moving forward. The first couple of plants we went through were relatively old and had very kind of basic controllers, and they were kind of set in their ways. However, we have seen some plants. I'd say the last 2 we went to, or the last one we went to, where it was clear that they were more, like far more interested in implementing and applying kind of newer control strategies, and we could see that in how they were operating currently, and like how much they had already changed over the last couple of years.
Great, thanks.
Rafael, we have a question in the chat from Michael from University of Utah. So he's asking, how would you incorporate variable flow capacity on the pumps into the model you're working on?
So let me not disturb the window too much. So I guess my question is, are you talking about, or Kelly, would you read that again?
How would you incorporate variable flow capacity on the pumps into the model you're working on?
Well, I guess I'm not sure what he means by incorporating it. We have models for both types of pumps. What we were looking at and what we thought initially, and what we still think, is that this obviously makes a lot less sense to be so being able to use the MPC controller with a series of pumps becomes less useful the more control you have on individual pumps. So if you're using variable speed pumps, we think we'll see less savings at that level. And that's okay for us, because as we've seen, there's still a lot of facilities out there that are using fixed speed for a lot of these things for most of the pumps. So as long as those are there, and those are there or are going to be there for the next 5, 10, or 15 years, then there's still significant potential savings that we could see. I'm not sure if that didn't directly answer your question.
Oh, thank you. It did. I appreciate it.
All right. Any other questions?
Rafael, this is Ryan again. Yeah. Another question I have is when you calculate the savings by adding VFDs, do you incorporate the cost for cooling those VFDs?
No, that's not something we have looked at, and we have kind of thought about, or I have thought about incorporating some of these other costs to give a more general idea of how useful this type of implementation would be. There's other things to consider as well, in terms of even switching from how they're currently controlling these pumps to some other type of controller where you're either having them cycle a lot more often or with a lot more frequency. That could also translate into maintenance or other types of costs that we're not currently taking into account. But that is something we should look at.
Thank you. Thank you. I appreciate it.
Sure thing.
We have another message question in the chat.
Mhm.
It says your model shows several input variables in the model. How do you manage / incorporate all of the input variables in the MPC?
Here, I'll go back. So yes, the MPC has several inputs going into it. In this picture, the kind of pink red ones are coming from the plant, right? You have a set of reference set points and some of the data points used as reference for what we're trying to do, and then there's an external flow rate or measured disturbance going into the controller that also goes into the tank model. Those are essentially the three most basic ones you need. There are extra ones, and we're using MATLAB Simulink to go through these models and figure that out. And essentially, if we're talking technically, there's a wealth of information on how to kind of work with MPC controllers in Simulink. It's not, there's a lot to it, and it's very in-depth. Yeah, essentially that's kind of it.
All right, thank you.
Anyone else have questions? You can definitely write them in the chat if you do, or just turn your mic on.
And if anybody has lingering questions and wants to contact me, my email is right there, and I'm sure Kelly is able to give you guys that if anybody wants.
Yep, for sure. All right, if we have no more questions, then thank you, Rafael, for presenting. And if anyone thinks of questions after, feel free to either email me or Rafael directly.
Thank you, guys.